Hello, good day to each and everyone. As promised in our previous video, we are now going to have our part 2 of our lecture presentation all about the different types of chemical reactions. For this video, we will focus more on another important concept when we observe in writing and balancing chemical equations. So sit back, get ready with your pens and your notebooks. Get ready to write down some important informations that we will be sharing for this lecture presentation. So without further ado, let us begin with our discussion. A very important consideration when we write a chemical equation is that we must observe how to balance each side of the equation. And that is why, for this video, we will deal with writing and balancing chemical equations from different types of chemical reactions. So, which leads me to our discussion for this afternoon. When we balance chemical equations, we always have to think of this very important concept which we talked in our previous video presentation. And what I mean by that is this very important law in chemistry, which is the law of conservation of mass, wherein you can interpret it as this: the mass of the reactants must always be kept constant, or the mass of the reactants must always be equal to the mass of the products. Or you may interpret it as the number of molecules on the reactants side must be equal to that of the products side. Okay, so let's make these concepts very clear as I show you some examples in this video. So I hope that you are getting ready with anything that you have there. You write these very important information because this will be a very important concept. Now, if you miss this, you might get confused. So you listen and follow through our discussion for this video. Okay? So if you're ready, I'm going to move on right now. Let's take a look at this example. An iron reacts with oxygen, yields a compound which is Fe2O3, or we will call this as ferric oxide. Clearly, this is not a decomposition reaction. Okay, so let's let's correct that one right now. Okay, so this is another typographical error, so forgive me if I haven't seen this ahead. This is not a decomposition reaction, but this is a combination reaction. Okay, so I hope that it's corrected already. How do we know that this equation has observed the law of conservation of mass? Now, a very simple trick that you can use in order for you to know that this equation is observing the law of conservation of mass is that we do a simple accounting of each of the number of atoms of the elements that are involved in this reaction. So let's take a look. How do we do that? Well, for me, it's always been like this. I always do this. I cut this into two, and then I just write all the elements that are involved in the chemical reaction. So we have here oxygen, and we have iron on the left side, and of course on the right side we also have iron and oxygen. Now what I usually do is that I count the number of atoms of each of these elements. So how do I count that? First, Fe, as you can see, Fe here has no coefficients, has no subscripts. So that means I can count this as one atom. That's one. Okay, how about the oxygen here? On the left side, you can see that there is a subscript of 2, which indicates that this oxygen has 2 atoms in this equation. Now, how about on the right side? Now, if you look at Fe here, it has a subscript of 2, which indicates that Fe here is of 2 atoms. So we write here 2. And oxygen with a subscript of 3 means it has 3 atoms. Now, if you're going to check the left and the right side of the equations, you can see that the number of atoms of each element in this equation is not the same. This will tell you that this equation has not been balanced at all. So, what can we do in order for us to observe balanced equation so that it will conform to the law of conservation of mass? Now, I will provide you some guidelines. Actually, there are a lot of methods that you can use to balance chemical equation. Now, for this lecture, I will be focusing more on the how do you call this? The trial and error method in balancing chemical equations. I can provide you some guidelines. I can also provide you some tips on how to do this. But in order for you to do that, you have to take note of this step by step. Okay, so I hope that you will go along with me. So if you're ready, I will be flashing on to the next slide. So what can we do in order to balance a chemical equation? Number 1, remember that diatomic elements should be written in their free or uncombined state. So what do I mean by a diatomic elements? These are elements that exist as 2 atoms in their free or uncombined state. So we have some examples here like hydrogen, it's always written as H2, oxygen is always written as O2, nitrogen N2, fluorine F2, Cl Cl2 for chlorine, bromine as Br2, and iodine as I2. They are diatomic elements. They should be written in their free or uncombined state, such as this. Okay, you cannot write them as a single H, especially if they exist alone in the equation. Unless if they are combined with other elements, you have to write them in their free or uncombined state. Okay, you have to remember that. Okay, next is you cannot change or manipulate the subscripts. That's a no-no. You cannot do that. Only the coefficients should be manipulated in a chemical equation. Coefficients also apply the distributive property when placed before compounds. That is, they are distributed in each atom of a compound. So for example, let me just show you an example. What do I mean by distributive property? Let's say, for example, I have here CO2. If I write a coefficient here, 2, that means that this 2 here is distributed to carbon and is also distributed to oxygen. So when you count the number of carbon atoms here, carbon here has 2. And how about oxygen? Now, usually you might be confused, sir. There is a subscript 2 in oxygen, and there is also a coefficient here. Now, in this case, all you need to do is just multiply the coefficient and the subscript. So as you can see, 2 coefficient distributed to oxygen, so that becomes 2. But since it has a 2 subscript, you have to multiply it with 2. So 2 times 2, so that means oxygen here is 4. Okay? So another example, let's say I will write 3 SO4. So that means that we apply the distributive property. That means my sulfur here has 3 atoms, and my oxygen here, since it's 3 distributed to oxygen with a subscript 4, all I need to do is that multiply 3 by 4, so that means it has 12 oxygen atoms from this compound alone. Okay, so that is how subscripts and coefficients work. The only thing that you cannot change in a chemical equations are the subscripts. The only thing that you can manipulate are the coefficients. Okay, so I hope that you understand that one. So another thing that you should take note is that this is just based on my experience. So balance first the elements that are neither oxygen nor hydrogen, because sometimes in most of the equations, hydrogen and oxygen occur in big numbers. So I'd rather focus first on elements that are neither oxygen or hydrogen. And also, you examine the compound on either side of the equation that contains the greatest number of atoms of an element other than oxygen or hydrogen. Again, other than oxygen or hydrogen. Okay? So why do I do that? I need to identify the element which has a greater number of atoms because usually I balance them last. Okay? Sorry, it's reversed. Usually I balance them first. So then after balancing them, I balance the hydrogen and then the oxygen, and the rest will just follow easily. Let me give you an example. For example, this is what we did a while ago. So Fe plus O2 yields Fe2O3. So as you can see, it is a imbalance or unbalanced chemical equation. What we can do to balance this equation is that, let me first choose my pen. We did an accounting a while ago. Fe and O is 1 and 2 here, and on the other side of the equation is 2 and 3. First and foremost, I would like to take a look on first Fe, because as what I've said, before I could balance the oxygen, I need to first look at other elements aside from oxygen or hydrogen, right? So I'm going to look at first Fe here. As you can see, Fe here is 1, right? You see that? Fe here is 1. And at the same time, Fe here is 2. So, which is not balanced here. So, since Fe in the left side of the equation is less than the number of atoms compared to the Fe in the second equation, so what we can do here right now is that maybe we can tweak, no? We can tweak the Fe on the other side of the equation. Now let's see the effect. Okay, if we place 2 as a coefficient here, okay, sorry for writing that one. Okay, let me erase that one for a while. Maybe it's much better if we will just rewrite the equation here. Fe plus O2 yields Fe2O3. Now, 1 and 2, right? So, they are unbalanced. But at the same time, if you look at oxygen here, it's 2 and 3. It's also not balanced. So it's a bit problematic here. So, let's try and test if adding a coefficient of 2 here works. Now, if I add a coefficient of 2 here in Fe, yes, if I add 2 Fe here, this Fe here now becomes 2, right? Because it has already a coefficient of coefficient of 2. At the same time, it's balanced. But our problem is O2 and O3 are not yet balanced here, right? So that means that we need to do something about this. Now, this is especially difficult, especially if one of the elements is attached to a compound. So usually what we do here, class, is that, for example, in this case 2 and 3, we usually look for what you call as LCD, least common denominator, right? So I'm going to look for an LCD of 2 and 3. What do you mean by LCD here? What is the least number that can be divided by 2 and 3? And in this case, it's 6, right? So 6 is the LCD of 2 and 3. So what are we going to do with 6? So we place a coefficient beside the element or beside the compound that will make the number of oxygen atoms become 6. Okay? So in this case, in our left side of the equation, so what coefficient am I going to place in oxygen in order to make this as 6? So I'm going to write here 3 O2. Okay. First, so that you will not be confused, I will just erase first the coefficient from the first example because when we tested it, it's a fail. So let's write first here 3O2. Now let's do an accounting. Fe here is now 1. Oxygen here, if you are going to multiply 3 times 2, that now becomes 6. Okay? Now let's go on the other side of the equation. Fe is 2 here, while oxygen is still 3 here. So let's look at the right side of the equation. What coefficient should we place on this compound so that the oxygen becomes 6 here? So clearly, we should place 2. So again, since we place 2 in a compound, this applies the distributive property. So we have to distribute this 2 to Fe also, as well as to oxygen. So since 2Fe, there is a coefficient in Fe here, which is also 2. So we are going to change this one right now. So Fe here now becomes 4. Okay? Because 2 times 2, that's 4. Then 2 times 3 in the oxygen now becomes 6. So as you can see, by doing so, we already balanced oxygen, which is now 6. Sorry, I placed 3 here. There should be no number 3 there. So that's a typographical error once again. Sorry for that. Oxygen is now 6. It's balanced. Now, what is not balanced here is Fe. So which is easier to balance? 4, we already have 4 on this side of the equation, and here we have 1. So I could just add 4 here as a coefficient so that we can balance this. So now this becomes 4, and now this becomes 4. So our final balanced equation here will be 4 Fe plus 3 O2 yields 2 Fe2O3. Okay, this is now our final answer. Okay, so this is usually how we do balancing chemical equation. Okay, now let's look at another example. Okay, this is a bit complicated with a lot of elements involved. Sir, it's so hard to account, sir. I don't know how to do that. How do we do this? Additional guidelines. When groups of atoms such as polyatomic ions like SO4, NH4, NO3 in the equation act as a unit and appear intact on both sides of the equation, you balance them as a group. What do I mean by that? Let me show you. For example, when I do an accounting, I wrote Mg because Mg is a metal. So Mg is 1, Mg is also 1 on the other side. Now, as you can see here, I wrote SO4 as a group. Because SO4, as you can see on the left side, is intact, and it's also intact on the other side of the equation. And since SO4 is a polyatomic ion, if you're going to check it in the periodic table of your elements, we can write them as a group. So that's why I wrote here SO4 1 and SO4 1. How did I know it's 1, sir? Now, if I'm going to place that in a parenthesis, you can see that they exist only as one group. So SO4. Okay, so there's only one SO4, and there's just one SO4 on the other side of the equation. How about NH4? NH4 is ammonium in your periodic table in polyatomic ions. NH4 in this side of the equation, let me enclose that with a parenthesis. Now, you won't be able to understand this unless you have a copy of your periodic tables with you. So you have to check on them. NH4 is ammonium, that is a polyatomic ion in the periodic table. Okay? So with a charge of +1, it's only 1, as you can see in this side of the equation. Now how about NH4 on the other side? As you can see, it's already enclosed with the parenthesis. It's a group. But in the NH4, outside of the parenthesis, there's a subscript 2 that indicates that there are 2 atoms of polyatomic ions for NH4. Okay? So that's 2. How about NO3 on the left side of the equation? So we can treat them again as a group here. NO3 is 1. And NO3 on this side, enclosed with a parenthesis, there's a subscript 2. That means there are 2 NO3 ions in that particular side of the equation. As you can see here, Mg is already okay, balanced. SO4 is already balanced. What's not balanced is this, NH4 and NO3. So what can we do in order for us to balance them? Okay, so very simple. Let's add some coefficients with them. So let's look at NH4 first. Okay? NH4 is 1 in the left side and NH4 is 2 on the right side of the equation. So, which is a lot easier for us to manipulate. Because you can see, I can add a subscript of, a coefficient of 2 here to make NH4 on this side of the equation as 2. But remember, as I add 2 as a coefficient here, it applies again a distributive property. So I distribute 2 on NH4 and I also distribute NO3 on the equation. So NO3 here now, instead of having 1, it now has 2 because I distributed 2. And by just adding 2 from that equation, as you can see, I made a miracle. This one is balanced, this one is balanced, this one is balanced, and this one is balanced. So our final balanced equation for this chemical reaction is MgSO4 plus 2 NH4 NO3 yields Mg NO3 the subscript of 2 plus NH4 with a subscript of 2 SO4. That is now our final balanced chemical equation. Now, there's one thing that I would like you to take note here. You can only include polyatomic ions as a group in balancing as long as they are intact on both sides. Okay? I hope that you will remember that. Okay? So, those are some of the guidelines that I could share with you when we balance chemical equations. But of course, all of this will mean nothing if we don't know how to apply this in other examples. So, let's have some further examples. So, let's take a look at this classic example. Mg plus Cl2 yields MgCl2. Okay, first, let's do an accounting. Always write that one as your first step. Do an accounting. Mg is 1 and Cl is 2 on this side of the equation. Let's cut that into half. Mg here is also 1 and Cl is the 2. And as you can see, by miracle, this equation is already balanced. So that means that we don't do anything from here. So if in the exam there's a blank here, all you need to do here is just supply it with a subscript of 1. A coefficient of 1. But anyways, by writing it as it is, that is already understood that there is already a subscript of 1 beside that equation. So that means that our final answer will be Mg plus Cl2 will be MgCl2. That is our final answer. So that means it seems like we did not even try our efforts to balance this equation. So that's very simple. So let's proceed to our next example. About this, N2 plus H2 is NH3. Let's do again an accounting. Always do not forget that. N here is 2 because of the subscript 2. H here is also 2 because there's subscript 2. How about this? N here is now 1. And H here now is how much? 3. Wow. This is a bit complicated. What are we going to do? First, before we balance the hydrogens, remember our rule. Before we balance the hydrogens, we first balance other elements other than hydrogen. So, I'm going to balance first nitrogen. So, as you can see here 2, and here is 1. I can just simply add a coefficient of 2 here to make this 2, right? Now, by doing so, as what I've said, we are distributing the coefficients to the compound. So, by adding 2 here, we do not only distribute 2 to the nitrogen, but we also distribute it to hydrogen. So since hydrogen has already a subscript 3 here, so it's just like multiplying it by 2. It now becomes 6. Okay. Now, nitrogen has no problem. It's already balanced. So what can we do in order to balance hydrogen in this case? Since 6 here is bigger than 2, so I will do something that will make this hydrogen become 6 on this side of the equation. So all you need to do is just supply it with 3 as a coefficient, because 3 times 2 is equal to 6. So as you can see, hydrogen is now balanced. So it's as if there is a 1 coefficient here. So anyways, writing N2 as itself is understood that there is a coefficient of 1 and the beside it. So our final balanced chemical equation will be N2 plus 3H2 yields 2 NH3. Okay, very good. So I hope that you are getting this slowly but surely right now. But of course, let's further add more examples. Okay. How about this? Wow, sir, it's getting somewhat difficult, sir, huh? Okay, now there might be a typographical error here as I spotted it just right now. So let me just correct this for a while. There should be a coefficient subscript of 3 here. Okay, there. It's our equation. So what are the coefficients that we need to supply in each blank here to make this balance? So again, very important is that we do an accounting. So we have here Ca. Ca. Now as you can see, there is a polyatomic ion here. So let's highlight that one. CO3, right? That's a polyatomic ion if you're going to look at it in the periodic table. So I'm going to write it as a group so that I won't have any confusion in balancing them later. CO3, by the way, let's cut it half for a while. So that's Ca. I also write here CO3. What are other elements that we did not include yet? Okay, Na and Cl, right? Na and Cl. Okay, I will also write here Na and Cl. Okay, now let's do an accounting for each of these atoms or ions right now. For Ca on this side of the equation, there's no subscript, no coefficient, so this is 1, as well as here 1. How about CO3? So you can see if we treat this as a group here on this side, no other coefficients or subscripts, so this is also 1. And CO3 here, when we complete them as a group, that is also considered as 1. Okay? How about Na? Na on this side is 1. Now as you can see, Na here on the right side has a subscript, so that means that's 2. Okay, because that's 2 subscript. Now Cl here is 1 and Cl here on the other side is 2. How do we balance this chemical equation? Again, first and foremost, my rule of thumb is balance first the elements that are neither hydrogen or oxygen. So that means we have to balance Na and Cl first. But how do we know which element should be balanced first? Now, my other rule of thumb here is that usually I go with the metals first. I balance them first. Okay, so let's try that one right now. Now, as you can see from this initial balance tallying, Ca is balanced, CO3 is balanced. Only 2 elements are not balanced, Na and Cl, right? So let's try balancing Na first. So since Na here has already a subscript of 2, which makes it 2, now in order for me to balance it, I need to put something, a coefficient that will make Na here as 2. Okay, so I'm going to place here 2 Na. So 2. So by doing that, I'm not only distributing 2 to Na, but I'm also doing it to Cl. So Na now is 2, and Cl right now becomes 2. And miraculously, by just adding 2 coefficient in NaCl, we balance the equation. So it's understood that this side of the equation has a coefficient of 1. So we can write it as 1 there. So as you can see, this is already a balanced equation. So our final balanced equation will be CaCO3 plus 2NaCl yields CaCl2 plus Na2CO3. Let me box that one for you. This is now our final answer. Okay. Now, I want you to try this one on your own. So once I flash this example on your screen, I want you to try this on your own. You may pause the video for you to practice this on your own, but if you want me to reveal the answer, you may as well stay in after I pause for 10 seconds. Okay, get ready. You may pause this video. For those who would like to reveal me the answer, just stay here. I'll wait for 10 seconds. Ready? Okay, for those who stayed with us, thank you. Now, let us balance this chemical equation. First, let's identify ions here. As you can see, we have hydrogen. Then we also have a polyatomic ion here, PO4. You can see it's intact on both sides of the equation. So I'm going to write hydrogen also here and PO4 here. Okay. Another element that we forgot, we have the K, right? Or the potassium. I think there are no other elements anymore. Oxygen, of course. Let's not forget oxygen. Okay, PO4, we treat this as a separate group. No? So PO4 here, since PO4 has one here and it has PO4 also here. And we also separate oxygen because there is an oxygen here in KOH and there is also an oxygen here. Okay, so I hope that you understand that one. Okay, now let's balance them and let's do a tallying first, rather. Okay, let's tally. H here is, as you can see, 1, 2, 3, and as including this one, it makes up to 4, right? So PO4 here exists as 1, so we write this as 1. By the way, we forgot the H2 here. So H2 here is, H here is 2 because there's a subscript of 2. Okay. Now K here is 1 and K here from the side is 3. And oxygen, additional oxygen is 1 and 1. Okay. There. Now, which of the elements are not balanced? So oxygen here is balanced, additional oxygen here is balanced, PO4 here is balanced. So what is not balanced is hydrogen and potassium. So let's balance them. So first, I would like to go as what I've said before you balance the hydrogen. If there are instances that there are hydrogens in your compound, you balance them after you balance the metal. So as you can see, my metal here is potassium, which is K. So K here on the right side is 3 and K here on the other side is 1. So in order for me to balance this, I will do some tweaking here in the potassium side, in the left side, to make this potassium on this side 3. So I'm going to write a coefficient of 3 here to make my potassium here 3. So it's like multiplying this by 3, which becomes 3. So by doing so, I'm also distributing it to the other elements, right? So my oxygen now times 3 becomes 3. And my hydrogen now, since I added 3 here and an additional 3 here, so this now becomes 6 if you're going to count. Take note, 3 hydrogens plus 3 hydrogens on this side is now 6. So as you can see, I balanced my potassium already. But by doing so, I did something that doesn't balance my oxygen and my hydrogen. So what I'm going to do right now is that I'm going to do something with my hydrogen. Okay? Now my hydrogen here is 6 and my hydrogen on the other side is 2. So what I can do to make this 6 is that I'm going to place a coefficient of 3 here. Now, by doing so, 3 times 2, my hydrogen here becomes 6. But I am not only distributing it to hydrogen. Since it's a compound, I should also distribute it to oxygen. You have to remember that. So my oxygen here now 3 times 1 is now 3. And as you can see, by doing just a little bit of tweaking, I already balance hydrogen and I already balance oxygen in this case. And I think the rest of the equations are already balanced. Okay, so this is understand. So since it's balanced already, it's understand that there is a 1 coefficient here and 1 coefficient here. But when we write the final balance equation, it's H3PO4 plus 3KOH yields K3PO4 plus 3H2O. Okay. And that is now perfectly balanced chemical equation. Okay. So I hope that you got that one. All right. Now, moving on to another example. Okay, try this on your own. I'll give you 10 seconds. You may pause the video. For those who want me to reveal the answer, you may remain and watch how it's done. Okay, so I guess we can now reveal our answer. So, in order for it to balance again, don't forget, let's do a basic accounting. K, B, and O, since they are the only elements involved in this reaction. K, B, O. Okay. K here is obviously just 1. Well, boron is 2 here, and oxygen is 3. Now, K here is also 2. Boron is 1. Oxygen is also 1. Now, good rule of thumb. When you balance this, first, always balance the metal element. Okay? So, when we balance the metal element, let's try balancing the metal element right now. Now, when we balance the metal element here, we can just simply add 2 here. And we did nothing to the others. We only balanced the K, but we did not affect the other one. So technically, if that happens, then that means that our first step is not going to work. So we are going to go to option B, which is to balance boron. Now, boron is 2 here. So to make this side of the equation 2 borons, so I need to add 2 here. But by doing so, I'm only affecting the boron. So that won't work either, because oxygen is still 3 and oxygen is 1 on the other sides of the equation. So what we can do right now is this. We have to consider oxygen here. Okay? Oxygen is 3 here and oxygen is 1. So since 3 here is bigger than 1 on the other side of the equation, I can just add a 1. I can add a coefficient of 3 to make my oxygen here as 3. Okay? But by doing so, I'm also affecting my potassium, right? So that becomes 3 times 2. So here, this becomes 6, right? Now, by doing so, we affected potassium and oxygen. So oxygen now is balanced. Now, by doing so, we affected the potassium, which is now 6 here. So to make this potassium 6 here, I'm going to place a coefficient of 6 here. 6K. So that it becomes 1 times 6, it becomes 6. Okay? Now how about the boron? So since boron here is 2 and boron here is 1, so I can just add a coefficient of 2 here to make this 2. So as you can see, this is now a balanced equation, and this is considered as a coefficient of 1. So when we write the balanced equation, it becomes 6K plus B2O3 yields 3K subscript 2O plus 2B. And this is now our balanced equation. Okay? So I hope that we are making things clear so far. So far I've provided a lot of examples already. So now let me provide another example before. I think that's the final example already. So that's how you technically balance chemical equations for our different types of chemical reactions. So let me end our slide from here. So in general, when we balance chemical equations, we conform to the law of conservation of mass. And by doing so, we do not only make adjustments to the coefficients of the equations, but we also are affecting the number of molecules in the reactants and product sides, overall making sure that the mass of the reactants always is constant and always is equal to the mass of the products. That is why balancing chemical equations is very important, because in chemical reactions, the law of conservation of mass is always observed. Now, in order for you to practice this, please answer the activity that I placed in the running CLE under Module 3, Topics 3 and 4. Please answer the exercise on balancing chemical equations so that you can have practice or good grasp on how to balance chemical equation. Now, in case you don't understand it still, you may contact me personally, or you may rewatch our video presentation. Okay? So I guess that's it for this afternoon. So I hope that you learned something out from our discussion for today. So this has been a good day for us. In case of questions and clarifications, please do not hesitate to chat me. And for those who want to rewatch the video for you to understand more about the topic, you may do so. Okay? But in case that you still don't understand it, please contact me immediately. Okay? So goodbye everyone. Let us see you once again in our next video. See you, and God bless you.